Let us see examples. Let a, b, x, y be non-zero integers, and let we have the equation ax plus by is equal to 1. Then show that GCD of AB is same as GCD of XY is same as GCD of A with Y is equal to same as GCD of X with respect to B is 1. So we'll prove this solution. We have the numbers or integers a, b, x, y, and we have equation ax plus by is equal to 1. To show GCD of ab, GCD of xy, GCD of ay, GCD of xb which is equal to 1. So to show these numbers has GCD 1 means if we assume ax plus by has GCD d, then what will happen? Let's see. Suppose that GCD of A and B which is D. If D is GCD of A and B, then D should divide A and D divides B, right? Then by using definition of divisibility, then by definition what we say that D divides A and D divides B. Now D divides A and D divides B, then there exists then by using definition of divisibility, what we say, D is equal to dk1 and B is equal to dk2 for some k1 k2 belongs to set of integers, right? So here what we have given, ax plus by is equal to 1, right? Now using this value, so using values of a and b in equation, what is the equation? Ax plus by is equal to 1. So using this value a and b, so a has value dk1, b has value dk2, so we get dk1x plus dk2y is equal to 1. So I will write it as 1 is equal to, I will take d as a common into bracket k1x plus k2y, right? So I will write it as integers k. So 1 is equal to dk dash, where k dash is nothing but k1x plus k2y which belongs to set of integer. Then by using definition of divisibility, what we say, d divides 1, where d is the GCD, where d is GCD and d always greater than equal to 0, because g is always positive and greater than equal to 0. So here, sorry, strictly greater than 0, so d not equal to 0, GCD is always positive, right? So what is the possible values? That implies here value of d. So the number which is divisible by 1, which is only 1, then d will be 1, right? So value of d is nothing but 1, so GCD of a and b is equal to 1, right? So here d divides 1 and here d is GCD of a and b, that implies d greater than 0, so this must be value satisfy this equation will be d equal to 1. Thus what we say, GCD of a and b which is equal to 1. Similarly we have to show that GCD of x and y which is again 1. Similarly assume GCD of x and y is again d, then by using definition of divisibility, d divides x, d divides y, then definition x is equal to dk1, y is equal to dk2 so here k1 k2 belongs to set of integers. Then what is the equation? Ax plus by is equal to 1. So using value of x and y, which is dk1. So a dk1 plus b dk2 is equal to 1. So we will get 1 is equal to d into bracket a k1 plus b k2. So this is value of k dash. I will write d k2. So k2 is equal to a k1 plus b k2 belongs to set of integer. So I will get d divides 1. So d is gcd and d is always greater than equal to 0, means the possible value is nothing but d is always less than equal to 1 when d is exist, means d divides 1. So possible value which is less than equal to 1. So that's why we say that d is equal to 1 is only possible value. So d is equal to 1 means what? GCD of x and y is equal to 1. So GCD of x and y is equal to 1. Similarly, you can see GCD of ay and GCD of xb is again 1. For assuming value of GCD of ay which is equal to d and GCD of xb again d, then solve like this, we will get solution. Let us see another example. I will take, if GCD of a m is equal to 1 is equal to GCD of b and m, then show that GCD of a into b with respect to m is same as 1. So we will prove this, that is if a and m are relatively primes and b and m are relatively prime, then show that ab with m is relatively prime. So solution. So here now what we have given, a m is equal to 1, instead of a m is equal to 1, then by using GCD theorem, there exists x naught y naught belongs to set of integer such that, so how to write, a x naught plus m y naught is equal to 1, right? So we have to prove that a into b. So I will write this equation as a x naught is equal to 1 minus m y naught. This is equation number 1. Also what we have given, GCD of b and m is equal to 1. Then again by GCD theorem, there exist integers x1 y1 belongs to set of integers such that, how to exist, here bx1 plus m y1 is equal to 1. So I will solve this for value of bx1. So we will get bx1 is equal to 1 minus m y1. So this is equation 2. So we will multiply equation 1 and 2 corresponding sides. So what will we get? So multiply equation 1 and 2 corresponding sides. What will we get? Here a x naught and here b x1 is equal to 1 minus m y naught into 1 minus m y1. So here I get a into b x naught x1, which is equal to, here after multiplication we will get 1 minus m y1 minus m y naught minus plus m square y naught y1. So I will take m as a common between these two. So I get here 1 minus m into bracket y1, I have taken minus sign common, plus y naught plus m y naught y1, and left side is a into b x naught x1. So I will write this as value y2. So here a into b x naught x1. So 1 minus m into y2. So this is y2, where y2 is nothing but y1 plus y naught plus m y naught y1 belongs to set of integers. Now this is minus, so left side I will get positive. So a into b x naught x1 plus m into y2 which is equal to 1. Then by GCD theorem, what is GCD theorem? If d is equal to ax plus by, then we write it as GCD of a and b is nothing but d, right? So here a into b x naught x1 plus, so this can be written, so x naught x1 are the integers, so I will write it as x2, right? So I will write this as x2, so a into b x2 plus m into y2 is equal to 1, where x2 is equal to x naught x1 belongs to set of integer. Then by using definition of by using theorem, then by theorem what we say, then by theorem, this is theorem that if GCD of a and b is equal to d, then we write d as GCD, ax plus by. Means there exists x and y such that ax plus by is equal to d, or we write this as d is equal to ax plus by, then GCD of a and b is equal to d. So we write it as GCD of a into b and m, which is 1. Hence the proof. Then by theorem, GCD of a, b and m is equal to 1. Let's see another example. If p is prime number such that p divides a and p divides a square plus b square, then show that p must divides b. So here p is prime number, so here what we have given, here p divides a, then by using property p divides a, then p must divides a square, right? P is prime numbers, p divides a, then p must divides p square. For example, 5 divides 5, then 5 also divides 5 square, right? So we have write this like this. And also what is given, p divides a square plus b square, then we have the property that if c divides a and c divides b, then c must divides a plus b or a minus b, right? So here p divides a square, p divides a square plus b square, then what we say, p divides a square plus b square minus a square. So p also divides subtraction of these two, means a square get cancelled, so p divides b square. So here we have p is prime number, so 5 divides, suppose b square is nothing but prime numbers, find prime number square. Here 5 divides 25, means 5, what we say 5 divides 5, because 25 is 5 square, means 5 divides 5, so p divides b square, then we say that p divides b. Now in next point we will see congruences. So we continue the study of divisibility, but for a slightly different point of view. A congruence is nothing but more than statement about divisibility. However, it is more than just a convenient notation. Let's see congruences. So definition of congruence mod n. So congruences. So congruence modulo n. Let's see definition. Congruence modulo n. So the definition of that. Let a and b be any two integers. So the definition is, let a and b be any two integers and n is greater than 1. Be an integer if n divides difference of a minus b. If n divides a minus b, then we say that a is congruent to b modulo n. We say that a is congruent to b modulo n. operation modulo n. So this is the meaning for if n divides a minus b, then we see that a is congruent to b modulo n, and we write and we denote or we write it as a is congruent to b modulo n. So this is notation. Suppose if n divides a minus b, then it can be written as a congruent to b modulo n. So clearly this defines a relation in the set of integers and called congruence relation modulo n. So this defines a relation in set of integers z, and called congruence relation modulo n, called congruence relation modulo n. So thus, so we have a congruence to b modulo n, which is nothing but, so a congruence to b modulo n means what? This is if and only if case, means n divides a minus b, or then by using definition of divisibility, what we have, n divides a minus b, then so we have b divides d, means what? There exists integer k such that d is equal to b k, right? Like this, here I get a minus b is equal to n into k for some k belongs to what? Set of integers, right? So this is definition. For example, so here 11 is congruent to 5 modulo 6, because here difference of these two, 11 minus 5, which is 6, and 6 divides 6, right? And 6 divides 6, so that is what we say, 6 divides 11 minus 5, therefore this is congruous. Next again, similarly I will take minus 7 is congruent to 10 modulo 17. So here difference of these two, here minus 7 and here plus 10, so left side minus 10, which is minus 17, and minus 17 and 17 divides minus 17, that is 17 divides minus 7 minus 10, therefore this is congruence relation modulo 17, right? So let us see the properties of congruence modulo n. So some properties of congruence modulo n. So let's see theorem. So the statement, let a b c d x y denotes integer, then first, if a is congruent to b modulo n, then first show that ax is also congruent to bx modulo n, and second one, show that a plus x congruent to b plus x modulo n, and second question is, if a congruent to b modulo n and c congruent to d modulo n, then first one, a plus c congruent to b plus d modulo n. second, so here addition, so I will write subtraction. A minus C is congruous to B minus D modulo n. Third one, Ax plus Cy is congruous to Bx plus Dy modulo n. And last one, fourth, AC congruous to BD modulo n. So let us prove these properties or theorem. So proof of the theorem. So first, so what is given here? Here A, B, C, D, X, Y are set of integers, and first we have given A congruous to be modulo n, then we have to show these properties, right? So first let us see now. So I will assume this. So we have this definition, A congruous to be modulo n, not right? So here what we have given, A congruous to B modulo n, right? Then by using definition of congruence property, then n divides A minus B. Then by using definition of divisibility, A minus B is equal to n into k for some k belongs to set of integers, right? So I will use this. Now we have to show that here we have to show that Ax congruous to Bx, means what we have to show here, n divides Ax minus Bx, or I will write Ax minus Bx is equal to n into k, right? So this equation, using this equation, now I will consider or multiply both sides by x. Then what will happen? So multiply both sides by x, multiply both sides by x, then what will we get? Ax minus Bx is equal to n into kx. So I will write in bracket. So here I will write Ax minus Bx is equal to n into k dash, for k dash is equal to kx belongs to set of integer. Then by using definition of congruence relation, what will we say? N divides Ax minus Bx, and then by using definition of congruence relation, what we say? Ax congruous to Bx modulo n. Hence the proof of first part. So this is the proof of first part. Now second part, to prove second part. So here A plus x congruous to B plus x modulo n operation, right? So we have what we have? So we have the relation here. What we have? A minus B is equal to nk. So A minus B is equal to n into k, right? So I will adjust here x, and here is also x. So I will adjust that A plus x minus B minus x. So here plus x minus x cancel. So remaining term A minus B, which is equal to n into k. I have taken adjustment plus x and minus x. So I will write it as A plus x. I will take minus sign as a common. B plus x, minus sign common. So here is B, which is equal to n into k. Then by using definition of divisibility, what we say? N divides here A plus x minus B plus x. Then by using definition of divisibility, what we say? A plus x, which is congruous to B plus x modulo n. Hence the proof of second part. Now for second, let's proof of second part. So here again what we have? A, B, C, D, X, Y belongs to set of integer, and what we have here? A is congruous to, so second one. So this is proof of 2. Second, A congruous to B modulo n, and what we have here, C congruence to D modulo n. So we will prove this theorem. Now here A congruous to B modulo n means what? What is definition? N divides A minus B, and C congruous to D means what? N divides C minus D. Then there exists K1 such that A minus B is equal to N into K1, and here C minus D is equal to N into K2 for some K1, K2 belongs to set of integers, right? So now what we have to prove here? A plus C is congruous to what? A plus C congruous to B plus D. Now we will assume this property. So we will prove first. Now assume, so here left hand side is A plus C and right hand side is B plus D. Now A plus C, I will take this side as left hand side, A plus C minus B plus D. So this can be written as, so here A plus C and minus B minus D. So I will take A plus C minus B minus D. So I will write it as A minus B plus C minus D. So we have the value of A minus B. So value of A minus B is nk1 and C minus D has value nk2. So here this is nk1 plus nk2. Therefore what we get? A plus C minus B plus D, which is same as, I will take n as a common between 2. So n into k1 plus k2. So I will write n into k dash, where k dash is equal to k1 plus k2 belongs to set of integers, right? So I get here left side A plus C minus B plus D is equal to n minus k dash. Then by using definition of divisibility, we will get n divides A plus C minus B plus D. Then by using definition of congruence, what will we get? A plus C is congruent to B plus D modulo n. Hence the proof of first. Now second, let's prove second part. Now we will assume here, so this is second part. So A minus C minus, so this part is left hand side, so A minus C minus B minus D, which is equal to, so I will write it as A minus C, so minus B minus minus plus D. So I will take adjustment, so A minus B, so here which is A minus B, so minus C plus D, right? So I will take here A minus B as it is. I will take minus C, minus sign is common, so C minus D. So we know that value of A minus B is nk1 and C minus D has value nk2. So we will get, so left hand side is A minus C minus B minus D, which is equal to, so has value nk1 minus nk2, so which is equal to n as a common, so k1 minus k2, so which is equal to n into k dash, where here k dash is equal to k1 minus k2 belongs to set of integers. So here left hand side A minus C minus B minus D. So then by definition n divides A minus C minus B minus D, right? So then by using congruence definition, so A minus C is congruent to B minus D modulo n operation. Hence the proof of second property. So first, second is done. Now we will see third property. Let's consider third. So I will write it as, so here I write ax plus cy minus this minus bx plus dy. So we have to prove this. So ax plus cy left hand side minus right hand side, which is equal to, so I will solve this. So ax plus cy minus bx minus dy. So I will take x as a common, so what will we get? A minus b into x plus in these two I will take y as common, so c minus d into y. So we know that value a minus b has value nk1, so which is equal to nk1 x plus c minus d has value nk2 y, right? So here left hand side is our left hand side ax plus cy. So a plus cy minus bx plus dy, which is equal to, I will take n as a common, so into bracket k1x plus k2y. So I will write it as n into k dash, where k dash is nothing but k1x plus k2y, which belongs to set of integers. So I get ax plus cy minus bx plus dy, which is equal to n into k. Then by using definition of divisibility, we will get n divides ax plus cy minus bx plus dy. Then by using definition of congruence relation, so we get ax plus cy is congruence to bx plus dy modulo n. Hence the proof of third property. Now we will prove last property. Now to prove here AC congruous to BD modulo n. So I will take AC minus BD, which is equal to, so I will make as change. So AC I will take adjustment. So here is C, I will take common element between these two. So I will take B and C. So I will subtract BC and add BC minus BD. Add and subtract BC. So here BC and minus BC cancel, so remaining terms as it is. So I will take C as a common. So A minus B into C plus I will take B as a common. So into bracket C minus D into common is B. So left hand side AC minus BD is equal to, so A minus B has value nk1 into C plus C minus D has value nk2 into B. So I will take n as a common, in bracket k1c plus k2b. So AC minus BD, so I will write AC minus BD is equal to n into k dash, where k dash is nothing but k1c plus k2b, which belongs to set of integers. So I get here AC minus BD is equal to nk. Then by using definition of divisibility, we get n divides AC minus BD, and by using definition of congruence modulo n, so AC is congruous to BD modulo n. So here we get the proof of fourth. Now in next lecture we will see another properties of integers under congruence relation. Thank you.